Hello everyone and welcome to Digital Signal Processing and Discrete Time Control tutorials. In this tutorial we will cover one very important topic for properly understanding digital signal processing and control algorithms. Namely, we will explain the concept of Z-transform. Some people pronounce Z-transform as Z-transform. However, in this video tutorial I will say Z-transform. Here is a brief outline of this video tutorial. First, we will define the Z-transform. Then we will learn how to compute the Z-transform of several typical and very important sequences or signals used in digital signal processing and control. Namely, we will learn how to compute the Z-transform of the unit impulse sequence, delayed unit impulse sequence, and the unit step sequence. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this video tutorial, as well as more than 400 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start. Before starting with examples, it's very important to properly understand and memorize the definition of the Z-transform. In this tutorial, we consider sequences that are zero for negative values of the discrete time instant. Consequently, we consider the unilateral Z-transform defined like this. Let y of n be a discrete time sequence. Y of 0, y of 1, y of 2, etc. Over here, y is the signal and n is a discrete time instant that can take values 0, 1, 2, 3, etc. Then the unilateral Z-transform of this sequence is defined like this. Capital Y of Z is equal to this sum where n goes from 0 to infinity of this general term, y of n multiplying z to the power minus n. Let us now expand this sum. For n is equal to 0, we obtain y of 0 multiplying z to the power 0. Then for n is equal to 1, we have y of 1 multiplying z to the power minus 1. For n is equal to 2, we have y of 2 multiplying z to the power minus 2. And we continue like that. This sum is actually equal to y of 0 multiplying z to the power 0 is actually 0 plus y of 1 multiplying z to the power minus 1 plus y of 2 multiplying z to the minus 2 and plus. Over here there are several things that we need to keep in mind. First of all, z is a complex number. It has a real and imaginary part. So always keep in mind that when you see z in the Z-transform, z is nothing less than a complex number. Then let's explain this notation. Capital Y of z. This notation is the complex variable obtained after the Z-transform of the discrete time sequence. So what the Z-transform is actually doing, it's taking this sequence and it converts this sequence into a complex number, or the expression involving complex number, which is essentially again a complex number with its real and imaginary parts. Keep in mind that thing. We use lowercase letters, such as letter y, to denote the sequence in the time domain. However, we use capital letters to denote its z-transform. As I mentioned previously, the z-transform transforms signals from the discrete time domain to the complex z-domain. On the other hand, the Laplace transform transforms continuous time signals to the complex s-domain. The Laplace transform is used for continuous time linear systems. On the other hand, the z-transform is used for discrete time systems. That is, what Laplace transform is for continuous time system, that is the z-transform for discrete time systems. Let's explain another important notation. Often in literature, you'll see this notation. This calligraphic z of y of n. This notation is used to denote the z-transform, and this notation is actually equal to capital Y of z. The sum in this definition is an infinite sum, and naturally the question of convergence of such a sum might arise. In this tutorial, we will consider sequences for which this sum converges. In our future tutorials, we will analyze the convergence in more detail. Z-transform is a very useful tool for stability analysis, filter design, control system analysis, and design of discrete time systems. Consequently, if you are working in the field of digital signal processing and real-time control, or if you are a student studying electrical engineering or mechanical engineering, you need to have a very strong understanding of the Z-transform. That's why I'm making this tutorial, to help you to better understand the Z-transform. Next, let's learn how to compute the z-transform of some typical and commonly used sequences and signals in digital signal processing and control engineering. The first sequence or the signal is the unit impulse sequence. Unit impulse sequence. This sequence is defined like this. Delta of n is equal to 1 when n is equal to 0 and 0 when n is not equal to 0. Let us graphically represent this sequence. On the horizontal axis, I will place n, that is the discrete time, and on the vertical axis, I will place delta of n. Let's look at this definition. Delta is 1 when n is equal to 0. That is, when n is equal to 0, when we are here, delta is equal to 1. When n is equal to 1, delta is equal to 0. When n is equal to 2, delta is equal to 0, etc. The unit impulse sequence is very important in control engineering and digital signal processing. This sequence is used to determine the impulse response of the system. Let's illustrate this. Let this box or this block represent a system, S. The system has an input and has an output. As an input to this system, we will plug in a delta of n. That is, we will put this sequence. When time is equal to 0, we will send a unit impulse. It can be 1 or scaled version of 1. Then the system will react, and if it's a dynamical system, you will see the impulse response. The response of the system in time can, for example, look like this. Or it might look like this. or you might even get unstable response. If we know the impulse response of the system, we can actually determine the transfer function or the model of our system. Now let's learn how to compute the z-transform of the unit impulse sequence. Let's use the definition. Z of delta of n is equal to this sum. Sum, when n goes from 0 to infinity, delta of n. And as the result, we obtain delta of 0 multiplying z to the power 0 plus delta of 1 multiplying z to the power of minus 1 plus delta of 2 multiplying z to the minus 2, etc. Stop here and go back to definition. We can see that delta of n is actually equal to 1 only when n is equal to 0. This means the following. This term over here will be actually equal to 1. Multiplying z to the power 0 is actually 1. Plus over here we will have 0 multiplying z to the power minus 1 plus 0 multiplying z to the minus 2, etc. Since all the other terms are actually equal to 0, as the result we obtain 1. Consequently, the z-transform of the unit impulse sequence is equal to 1, and that's it. How about the z-transform of the delayed unit impulse sequence? The delayed unit impulse sequence is defined like this. Delta of n minus m is equal to 1 when n is equal to m, and it's equal to 0 when n is not equal to m. Let us graphically illustrate this sequence. Here it is. Over here is n, and over here is delta of n minus m. Let's see what happens over here. When n is equal to m, for example, over here, we have 1. Consequently, delta of n minus m will be equal to 1. For all other values of n, we have zeros. And this is very important. This sequence is called delayed since the original sequence is defined by having 1 over here for n is equal to 0. So we delay this sequence for m times steps, and consequently we obtain this sequence. To compute the z-transform of this sequence, we apply the definition. We need to compute z of delta n minus m. This is equal to the sum where n goes from 0 to infinity of the general term, n minus m, multiplying z to the power minus n. Let's compute this. This is equal to, let's see, delta. Now over here, n takes 0, so we have delta of minus m, multiplying z to the power 0, plus, then the second term is obtained when n is equal to 1. I have 1 minus m z to the power minus 1, plus I have delta 2 minus m z to the power minus 2. And if I continue like this, I'm just adding the term until this term. When n is equal to m, the general term will be delta of 0, and over here we will have z to the power, because n is equal to m, we will have minus m. And we continue further. The next term will be delta of 1 multiplying z minus m plus 1, since n is equal to m plus 1, and we continue. Now let's analyze this definition. We can see that the term over here is actually equal to 0. This is because delta of n minus m is equal to 0 for all the values of n that are different from m. Similarly, the second term will be equal to 0, the third term will be equal to 0, plus we will have the 0 terms. Then this term will obviously be equal to 1. This is because when n is equal to m, delta of n minus m is equal to 1. So I will have 1, and over here I will have z to the power minus m. And by using this definition, we can conclude that these all other terms will be equal to 0. And consequently, the z transform of our delayed unit impulse sequence is z to the power minus m. This is actually a very important result that is often used in digital signal processing. The z transform of a delayed unit impulse is z to the power minus m, where m is the actual delay. From here, we have a very important interpretation of the z complex variable. Namely, when we multiply a signal y of z, for example, y of z, by z to the power minus m, in the time domain, we actually obtain a delayed signal. That is, we obtain y of n minus m. That is the signal y of n delayed for m steps. Another important sequence is the unit step sequence. This sequence is defined like this. U of n is equal to 1 when n is greater than or equal to 0, and it's equal to 0 for all other values of n, that is when n is smaller than 0. Let us graphically illustrate this sequence. On the horizontal axis, we place n, and on the vertical axis, we place u of n. U of n is equal to 1 for positive values of n, and we have 1 over here, then 1 over here, then 1 over here, etc. For negative values of n, that is over here, we have 0, we have 0, we have 0, etc. This sequence is very important in control engineering and digital signal processing since it's used to determine the step response of the system. That is, first time we encounter a system, we need to compute or to determine its step response. To determine the step response, we'll take our system, represented by this box over here, to its input, we will insert the unit step sequence, and we will observe the output. For stable systems, the output will look like this. It will have an oscillatory behavior, and then it will settle down. Next, let's learn how to compute the z transform of the unit step sequence. Let's apply the definition. Calligraphic z of u of n is equal to, let's see, sum when n goes from 0 to infinity, u of n multiplying z to the power minus n. This is the general definition, and let's expand this definition. We have u of 0 multiplying z to the power 0, then we have u of 1 multiplying z to the minus 1 plus u of 2 multiplying z to the minus 2, etc. Now let's substitute the values. Obviously we have z to the power 0 is 1, and this term is 1. Consequently we have 1. Then plus we have u of 1 is 1, we have z to the power minus 1. Then this term becomes z to the power minus 2. Then the fourth term is z to the power minus 3 plus z to the power minus 4, etc. We can write all these terms by using the sum notation. We have a sum where n goes from 0 to infinity, and we simply have z to the power minus n. And that's it. Now, does this sum look familiar? Have you seen this sum somewhere before? This equation representing the z transform of un is actually very similar to the classical geometric series of real numbers. In fact, we can use the formulas for computing the sum of geometrical series and the formulas for computing the sum of n first terms of the geometrical series to compute the z transform. First of all, let us consider the finite sum. S with a capital letter N is the sum of the first n terms. This sum is given by z to the power 0 plus z to the power minus 1 plus z to the power minus 2, and we continue the summation until z to the power minus n minus 1. We go until n minus 1 since we start from 0, and this will be the nth term. This sum is actually equal to 1 minus z to the power minus n divided by 1 minus z to the power minus 1. Over here, if we consider this as a geometric series, and if for the time being we forget that z is a complex number, z to the power minus 1 can be interpreted as the common ratio. The common ratio is the ratio of the two subsequent elements in a geometric series. For example, if I divide this element by this element, that is, if I compute something like this, z to the power minus 2 divided by z to the power minus 1, I will obviously get z to the power minus 1. Similarly, for example, if I divide the fourth term by the third term, I will again obtain z minus 1. That is, if I take any two subsequent entries of this geometric sum, and if I divide them, I will always obtain z to the minus 1. That is, I will always obtain the common ratio. Now, this is the finite sum. However, over here we have an infinite sum. So, can we somehow modify this formula such that we can compute this infinite sum? Well, we can. And here comes the beauty of mathematics. You can let n to go to infinity. By letting n to go to infinity, we take more and more entries inside of this sum. And we can write s infinity is actually equal to, let's see, obviously in the denominator I will have 1 minus z to the power minus 1. However, what I will get in the numerator? Now, under the condition that this series converges, and I'm not going to discuss the definitions in more details, I will just say this, that under the condition that the modulus of z is larger than 1, that is, for complex numbers outside of the unit complex circle that's represented like this in the complex plane, that is, for the complex numbers that are over here, this sequence, that is, this infinite sequence, will converge, and consequently, what will happen that this term, when n goes to infinity, z to the power minus n will go to 0. And consequently, this term will become 0, and I will obtain this expression. It's 1 over 1 minus z to the power minus 1. And this solves our problem. This means that this Laplace, or actually the z transform of u of n, is actually equal to (1 over 1 minus z to the power minus 1). And we can represent this sum like this. This is nothing less than z minus 1 divided by z, and over here we have 1. And consequently, this is equal to z over z minus 1. And this solves our problem. To conclude, the z transform of the unit step sequence is actually equal to z over z minus 1. And that's it. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.